Hello learners, this is Education Online program. I'm teacher Lily. I'm going to teach chemistry and our topic today is redox titration. So what is this redox titration all about? Redox titration is based on the reduction oxidation reactions, which is mainly on the reducing agent and the oxidizing agents. So we have redox titration. So redox titration is based on reduction, oxidation, reduction, oxidation, reaction, which is based on reducing agent and oxidizing agents. So when you are dealing with the redox titration, you need to remember that there is a reduction oxidation reactions, which is dealing with the reducing agent and the oxidizing agents. So the oxidizing agent here, these are the agents or the reduction that are going to take place and the oxidation that is going to take place during the titration. So we need to remember that there is always a reducing and oxidizing agent when we are dealing with the redox titration. So this oxidizing agent and reducing agent comes through the reduction oxidation reactions. So it means redox titration based on oxidation reduction reactions. So here we may see that we have known that the other titration or the other types of titration, there is indicators being used, for example in the acid and base reactions. But here you may see that there is whereby you can use indicators, and there is also those titrations whereby you will not use an indicator. So there are those reagents that may need indicators, and there are those which does not need indicators. So here we may see that in the reactions or in the titration process of redox titration, you may see that there is a redox indicator, and redox indicator here, or we can have potentiometers. We can have potentiometers which is used in place of the indicator, whereby when we have in acid and base reaction we have to add indicators in drops, but here we may use a meter, or we can use a redox indicators. We can have also a starch indicator, can be used in some of the reactions. Starch indicator when the endpoint cannot determine itself clearly, so we shall have a starch indicator. Or we can have sodium diphenyl amine. Sodium diphenyl amines can be used as an indicator in some of the reactions. So here we may say that redox titration, some of the reagents or some of the titration doesn't need an indicator, but there are those which need indicators. So indicators that can be used can be like a potentiometer, or can be starch indicator, or can be sodium diphenyl amine. So which of the indicators are we going to use in the titration of redox titration? In which type of titration are we going to use the potentiometer? Here the potentiometer is a meter whereby you have to put it into the content in the conical flask, and then it reads. When it reach the end point, the reading is stopped. So it means you have reached the end point. So we can have a potentiometer to determine the endpoint of the titration as when one of the substituent is the oxidizing agent. Here when the oxidizing agent when the oxidizing agent is potassium dichromate, when one of the reagent, the oxidizing agent, is potassium dichromate, we can use the first indicator, which is the potentiometer, or we can use the meter as an indicator. Potentiometer as an indicator. Potentiometer as an indicator. So we have the first indicator. We use it when potassium dichromate is the oxidizing agent. So when are we using sodium diphenyl amine? We are using it when the color change of the solution from orange to green is not definite. Therefore, we use an indicator such as sodium diphenyl. It means also the same with this potassium dichromate. When we are using it as an oxidizing agent, we can use potentiometer as the indicator, or we can use sodium diamine. We can use sodium diamine, diphenyl amines as one of the indicator. Either we can use the meter or we can use solution of sodium diphenyl amine. So here also, when we are analyzing wine for sulfur dioxide, we require iodine as an oxidizing agent. So when we are using iodine as an oxidizing agent, we are going to have a different indicator. Here in this case, we are going to use a starch indicator, and this starch indicator will give us a blue color, the end point. So we shall have a blue color when we use a starch indicator at the end point. This is a reaction whereby we can have iodine as the oxidizing agent. So in the first one, when we are using sodium diphenyl amine, we can have the color changes from orange to green. So we shall have change of color from orange to green when we reach the end point. So it means when the color changes to green, we have reached the end point during the titration. So here we shall have a blue color when we reach the end point. So it means we have reached to the end of point of your reaction. Then you record the reading and then you make a table as usual. We have the initial, the final volume, and then the use volume. So after that, we get the average of the volume used when we did all the procedure for the titration reactions. So some of the redox titration do not require an indicator. So in this case, we can have, when we have the oxidizing agent as potassium permanganate. So potassium permanganate, we are not going to use an indicator. Why? Because here potassium permanganate is purple in color. So it changes from purple to pink color. So when the titration changes from purple to pink color, we can have the end point, or we have reached the end point. So in this type of the reaction, on this type of the titration, we are not going to use an indicator. So in redox titration, we have those titrations whereby we are going to use an indicator, and there are those which we cannot use an indicator, as I've already listed. So when you have seen that potassium permanganate is one of the reagents in the titration, it means that you are going to take out the indicator, or you are not going to use the indicator. If we are using potassium dichromate as the oxidizing agent, we have to use either the potentiometer, or we can use sodium diphenyl amine S1 of the indicator. So if you are using iodine as the oxidizing agent, you have to remember that there is a such indicator to be added in order to reach the end point. So you need also to remember the color change when you are dealing with the different reagents. So for example, you can have an experimental example. Our usual experimental example, of course, when you're standardizing a solution, it means at the end you wanted to achieve something. So it means you need to know you want to know the mole, the number of moles that reacted, and also you need to know the concentration of the reagents, or the concentration of the ions that you have used. So it means here, when you have an example in this type of the reactions or titrations, we have to remember that this is redox titration, and you have to put in our mind there is oxidizing agent and there is reducing agents. So experimental example. Experimental example. So here you are provided with the solution Q. Solution Q. You are provided with the solution Q, and solution Q is also we are provided with solution P. You need to know that the solution P is acidified potassium permanganate. Acidified potassium permanganate. Acidified potassium permanganate is solution P. Acidified potassium permanganate is solution P. And solution Q is ammonia. Solution P is ammonium ion 2 sulfate. Ammonium ion 2 sulfate is solution Q. So it means the two solutions provided is ammonium ion 2 sulfate and acidified potassium permanganate. So you have to remember that this type of titration may not require an indicator. So we shall have the color changes from purple to pink. So when you are titrating, you have to remember the change in color from purple to pink. So we need to fill the burette with the solution P. Fill the burette with solution P, which is acidified potassium permanganate. So the solution in the burette, or the one we are going to fill into the burette, is potassium permanganate. So in this case, we have to remember that the color of the solution in burette is purple in color. So we shall have potassium permanganate, and this potassium permanganate is the oxidizing agent in this case. So we shall take 25 using a pipette. We are going to take 25 of the prepared solution of solution Q, which is ammonium ion 2 sulfate. So we shall have 25 centimeter cube of solution of solution Q, and this solution is going to be transferred into a beaker, and then later we are going to put it into a conical flask. Or rather, let us say that we have to transfer 25 centimeters using a pipette into a conical flask. So we know that a conical flask is a solution we are going to put under the burette, and what is in the burette is potassium permanganate. So after that, we start our titration until we reach the pink color. So here, when we reach the pink color, we have to remember that we are finished with the first titration. So we shall have to repeat it 3 times to get consistent values in order for us to get the final volume or the titration volume that we needed for potassium permanganate that reacted with the solution in Q, which is ammonium sulfate, iron sulfate. So according to the results here, or the samples provided here, is remember that we have the first titration, we have to remember that the first titration here was, and the initial volume, and then we have the final volume. So the number of the titration number 1, it gives us 16. It gives us 16.1, which is the final volume. The final volume for the first titration is 16.10, and then the average of the volume here will be 16.1. So we need to remember that we are subtracting the final volume, the initial volume, from the final volume. The second titration, we are going to start from 16.90. So we shall have 32.90. So we shall have at the end, or the final volume, the average we are going to get from subtracting initial volume from the final volume, we shall have 16.1.00. Sorry. Here we have that the volumes are almost the same, but we need to repeat it the 3rd time in order to know exactly what is the final volume or the average of the volume that we needed. So we have to start now freshly from 00, which is the initial volume for the 3rd titration. Then we shall have 16.90 as the final volume. So the last volume here, or the final volume, from subtracting initial volume from the final volume, we shall have the average in 16.90. So we have seen that 16.10 and 16.00 are almost similar, so we need to get the average for it in order for us to get the volume of the solution, or the volume of potassium permanganate in the burette, so that we shall know that this is the volume that reacted with the content in the conical flask. So we shall have the average. The average here, we're going to take the 2 titrations. It means we have 16.10 plus 16.00 divided by 2, because there are 2 titrations. Then the final volume here will be 16.05 centimeter cube. So this is the volume that reacted with solution Q. So what else do you want to do? We are going to get the number of moles of solution Q that reacted during the titration. So we shall have, the first thing, we need to remember to get the relative formula mass. The relative formula mass of solution Q, which is ammonia ammonium iron 2 sulfate, which is hydrated. You need to remember that this type of solution is the hydrated one, or the reagent is a hydrated ammonium iron 2 sulfate. So we shall have 6 molecules or moles of water in this type of the solution. So we shall have ammonium iron sulfate 2 and then 6 molecules of water. So what will be the relative formula mass for this chemical formula? We have to add the mass number of each atom here. So at the end, when we sum them up, we shall have the relative formula mass. We know that the ammonia is 14. So because it is in the bracket, it means we have 2 ammonia. We need to multiply by 2 plus hydrogen is 1. The atomic mass is 1. And then there are 4 atoms of hydrogen. It means we multiply by 4. Then we multiply again by 2. So we shall have 1 times 4. Then we multiply again by 2 plus iron, the atomic mass is 56. Sorry, it's 32. So we shall have, how many ions do we have? We have only 1 atom of iron in this chemical formula. So we shall have 56 plus 32. 32 is the atomic mass of sulfur. How many sulfur do we have? We have 2 atoms of sulfur in this chemical formula. So we have to multiply by 2 again, plus oxygen. There is only 4 atoms of oxygen, but the atomic mass of oxygen is 16. We multiply it by 4. 6 multiplied by 4. Then again we multiply it by 2, which is outside the bracket, plus 6 molecules of water. It means we have to multiply hydrogen. Atomic mass of hydrogen is 1, and then there are 2 atoms of hydrogen. We have to multiply 2 by 1 again by 6. So we shall have 2 multiplied by 1 into bracket. Then we have 6 plus the one of oxygen. Oxygen, how many atoms do we have here? We have only 1 atom of oxygen, which is 16, the atomic mass, multiply by 1, then again we multiply by 6. So when we add up all these values, we shall have 392 as the relative formula mass of compound ammonium iron sulfate hydrated. So this is, if you have 1 mole of iron 2, ammonium iron 2 sulfate, we shall have it to be 392 grams. So here ammonium iron sulfate hydrated is 392 grams. So 1 mole of it will give us 392 grams. So you have to remember that solution Q, we took 23.5 grams. To dilute it, we have taken 23.5 grams. It means it is in solid form, so we prepare it to become a solution. So this, we have to remember that 1 mole. So X mole of the same solution will give us 23.5 grams. So here we shall have to cross multiply in order to get the number of moles of 23.5 grams that has been prepared or used during the titration. So we have to cross multiply. Here when we cross multiply, we shall have a value, and this value will be the moles of ammonium iron sulfate. So we shall have X will be equals to 23.5 multiplied by 1, then we divide by 392 grams. So the number of moles here will be equals to 0.0599 moles. So this is the number of moles of ammonium iron sulfate that reacted during the titrations. So we shall have 0.0 was dissolved in 1 decimeter cube. So this value here, or this moles here, 0.0599 moles, was previously dissolved when we are preparing the solution. We dissolve it into 1 decimeter cube. So we need to multiply the number of moles here by 1 to give us the molarity. Dissolve in 1 decimeter cube. So it means that the concentration, therefore the concentration will be the same. So we shall have 0.0599 multiplied by 1, which is 0.0599 moles per decimeter cube, or we can change the unit into capital M, which is molarity. So what else are we required to do? We have to get 1 mole of ammonium iron sulfate was dissolved. It forms the following ions. So we need to remember that there is reducing ion and there is oxidizing ion. So we need to get the chemical equation. This we shall have that 1 mole of ammonia iron sulfate. 1 mole of ammonium iron sulfate was dissolved. It forms the following ions. So we have to dissociate the ion. We have iron sulfate, 6 molecules of water, which we need to remember that it is hydrated ammonium iron sulfate. So the equation here will be 2 ions, or 2 molecules of iron of ammonia, which is aqueous in solution, plus iron plus sulfate. So we are going to see that these are the ions that has been given out. We have ammonia, we have iron 2, and then we have sulfate ions. So 1 molecule of ammonium ion produces 1 molecule of this aqueous solution produces 1 molecule of iron 2. So we shall have that, but 1000 centimeter cube, 1000 centimeter cube of ammonium iron 2 sulfate will be equals to 0.059 moles. So previously we know that 1 mole of ammonium iron sulfate hydrated is 0.059 0.59. So 25 of this same solution will contain X moles. So we shall have X by cross multiplying, we get that 0.0599 multiplied by 25 centimeter cube, then we divide by 1000, will be equals to 0.00149. So this is approximately to 0.0015. So this is the number of moles when we took 25 centimeter cube. So we have also to see that in the third procedure, what is required, thirdly, we have to remember that the manganese iron plus iron, 5 molecules of iron plus hydrogen will give us ammonia, aqueous solid, manganese and 5 of iron plus 4 molecules of water. So we have to remember that we need to get the number of moles here. So the moles ratio of manganese to iron is going to be 1 to 5. So we shall have the mole ratio will be 1 to 5. So we require to get 0.003 moles of manganese iron. So this we got it from the moles here, then we divide it by 5. We divide it by 5. So at the end we shall get the number of moles of permanganate that reacted with ammonium iron sulfate. So we got 0.003 from this. We divide the number of moles and then by the ratio of the ions, so we shall get the number of moles of manganese. So in this way we have to calculate also the concentration, and at the end we shall reach the concentration that we wanted after getting the moles of manganese oxide. So we have come to the end of this lesson. Thank you very much. It's teacher Lily. Thank you again.